Okay, guys, so let's now look at the different, we talked about these different modes that we're in terms of the N MOSFET or P MOSFETs, again, very similar. All the voltages are complementary or kind of reversed from the NMOS. So let's look at these three modes of operation: cutoff, linear, and saturation. So if you look at the cross section, when you're in the cutoff, it's like I said, it's the same as being either in accumulation or in depletion. It means that your gate source voltage is too low. It's either zero or too low to create a channel here. So there's the channel essentially here is either doesn't exist or is positive. So no current flows from drain to source in an NMOS. And basically electrons are blocked from going from source to drain. So in this case, let's see. If I was going to draw our IV characteristics, if it's, VDS versus IDS, in this case, our V gate source is 0, right? So V gate source is 0. So if I was going to draw the graph, it will just be a straight line, no current would flow. So this would be for VGS is equal to 0. And let's see if I draw, if I draw VGS versus VT, again, VGS would just be 1 point here, I guess. It would be here. And again, no current would flow. With different VDSs, it'd just be sitting there. Sorry, I didn't mean to make it VT on this. I need to be making this IDS. Okay, so in this case, basically the gate source voltage is 0 or otherwise below the threshold voltage. So let me write that down. Or VGS is less than VT. And basically this device is off because there's no way for the current to conduct from source to drain. Okay, the next region, which we call the NMOS linear region, what's happened is the gate source voltage is higher than the threshold voltage. And you have basically you have the case of an inversion of a channel is started forming. So we have the channel has inverted, means you have negative charges under the gate because of the electron hole recombination, the electron hole generation. Electrons are generated and they go underneath this channel. Okay, and so initially now, the gate, when you look at V, if the drain is at a low voltage, at exactly the same voltage as the source, then the voltage from gate to source, the voltage at the channel is the same everywhere, right? So now here you have to worry about another thing in detail. So in the case of our MOS capacitor, the gate to channel voltage or electric field was the same everywhere along the channel. Okay, but now because we have a source and a drain, depending on the voltage of the source and the voltage of the drain, the potential along this channel could be different. Like for example, here, this potential is exactly at gate to source potential. So the gate to source, because it's almost at the source voltage. The potential here is V gate to drain voltage, because the drain is sitting here and it's sitting at a voltage. And this is sort of some average value between V gate source and V gate drain. So when V gate drain is equal to V gate source, you have the same potential everywhere. Okay, but remember we said the source is typically the the lower of the voltages between the source and the drain. So typically the source voltage is at a lower voltage, and typically it's at ground, and typically the drain is at a higher voltage. So if the drain is at a higher voltage, meaning it's closer in voltage to the gate voltage, the drain voltage and the gate voltage are similar or closer to each other, there's less of a potential voltage here. There's less of an electric field than it would be over here. Okay, so basically in other words, the channel starts sort of shrinking here. It starts getting cut off, not cut off. It starts getting choked off. Okay, so here if I draw what regions we're in, and I draw VDS, IDS, and let's say we pick a voltage right at VGS. Or I'll just pick a voltage. Well, I guess it's any voltage higher than V sub T, VGS higher than V sub T. So I'll just call that. So it'll be basically where the portion of the curve we're looking at is, if you remember, we said the NMOS current versus VDS, where VGS was a curve like this, but in this linear mode, as long as the channel is sort of complete all the way across, basically means as VDS goes from 0 to a higher potential to some voltage here, you basically have a channel that looks like a resistor, because you have electrons that are flowing from the source to the drain, and as my drain voltage goes up, you basically get more and more current. So more and more electrons are getting, the electric field this way gets higher and higher, and I get more and more current, electrons going here, and therefore more current going this way. The current's the opposite direction as the electron, because the electrons are negatively charged. Okay, what do I want to say here? So this basically goes up until VDS basically gets to be VGS minus VT. Okay, and this is like a magic voltage where at this point it's VGS, whatever that VGS is, whatever value this was. So remember, this is for a constant for a given VGS. Okay, as long as VGS is greater than VT. So as long as VGS is greater than VT, the transistor turns on, and we have current flowing from source to drain. And initially, as long as the drain source voltage is reasonably low or below VGS minus VT, there is a dependency of the current on the drain source voltage. And it kind of looks like a resistance. It's a nonlinear resistance. Okay. Similar to a linear resistance, but pretty nonlinear. Okay, so you're in this mode of operation. Okay, now at some point, basically the voltage here, this drain voltage, gets high enough. So this VGS stays the same. If you're looking at the curve here of VDS versus IDS at a given VGS. So at some point, as VDS is increasing, as long as VDS is increasing, that doesn't do anything to this side of the channel, because this is at the same voltage as V gate minus V source, okay, on this side. But on this side of the channel, as the gate source voltage, as the drain source voltage goes higher and higher, means the drain voltage is going higher and higher at some point equal to VGS minus VT. This channel pinches off, meaning there is no channel here on this side. Meaning that as you increase the drain voltage, you still get the current flowing. Current flowing, sorry, I keep drawing the direction of the current wrong. So the current's flowing this way. Means you still get current flowing or electrons going this way, but you no longer have control of that current with the drain. So we basically say that the current's been saturated. So this is this point here when you stop having an effect, the drain source voltage stops having an effect on VDS and the curve flattens out and you end up with this curve. And for different VGS values, you'll end up, as the VGS gets higher, this cutoff point gets higher, not a cutoff, sorry, saturation point gets higher. As the VGS value gets lower, this the saturation point gets lower. And at some point, the transistor turns off when the VGS is too low. Let's see, do I want to say anything else here? Yeah, so, and again, the magic voltage is VD, and we call that VD sat, or the saturation drain voltage, is VGS minus VT. Okay, you'll see that that's sort of, that'll be, and then anything is, if VDS is less than VD sat, then it's in linear operation, or this part of the curve. And if VDS is larger than VD sat, we're in saturation. And we're on this part of the curve. Okay, so now so we have this, again, we have this curve of VDS versus IDS, and for various VGSs, so VGS1, VGS2, VGS3, we have different curves, family of curves. Now, let's try to see if we can give some, like a first level quantitative value to what these currents might be. Okay, so we basically have, so this is current. Okay, and basically current has really two parameters that we need to calculate. So if you look at the current, it's basically charge and how fast is the charge traveling. So how fast is the charge going across this from the drain to source? Okay, so basically you need to figure out how much charge is going through here, and then how long does it take to get from here to here? How long does it take to cover that distance? Okay, so so here is like this is like a real first level calculation of what this looks like. The charge of this channel, so this is like a pretty basic equation describing charge. The charge is the capacitance times voltage, if you just look at the charge on a capacitor, say. Okay, so we have, we know the capacitance, and we can calculate the voltage, or let's actually take a look at what these different values are. So if you just think of the channel, the capacitance is pretty much the capacitance of this gate oxide. Okay, so if you look at, if I zoom in here, this capacitance is this area, the area of this plate, okay, area times the permittivity of the material, the oxide, over the thickness of the oxide. Now, when we draw a transistor, so from the side, we usually draw the transistor from the side. So we look at this, the source and the drain, and the gate, polysilicon gate. And so the difference between, so the geometry of the channel is the separation between the source and the drain is known as the length. We usually don't look at what happens in this direction, but basically you can adjust this, and which is called the width, which is how long the source and the drain run along the gate. I can make this gate longer if I want, as long as I get the source and the drain to be longer. Sorry, that was a poor drawing. So I can basically adjust the W as much as I like. We typically don't draw that, but you can just draw it, make this thing bigger or make it smaller. So I can break down this area into the width times the length of the transistor times epsilon oxide over T ox. So now we'll talk about something that you see a couple of times in circuit design, CMOS design, effectively. One is that for any given process, we want to kind of simplify the amount of constants that we carry, because there's, for calculations, etc. So now in a given process, T oxide is constant. It's different in every process, but the thickness of this gate, the thickness here, is, if you're in a particular process, the manufacturer is building a particular transistor over and over again for you, they're going to try to keep that thickness the same. It's not like as a designer, you have an option to change that thickness. So you can basically assume that's constant for the process you're in. Okay, so this is in a given process, the oxide is constant. And then epsilon oxide, which is the dielectric constant or permittivity of silicon dioxide, is of course constant. And I believe it is, if I can remember right, it's 3.9. I'll have to check this for you guys. And that's multiplied by the permittivity of free space, farads per meter. So this is epsilon naught. Okay, so this is constant, this is constant. So we can, to make our life a little easier, for each process we're in, okay, they've defined for each process they have defined a parameter called C ox, which is just this epsilon ox over T ox. Okay, so this you can write as WL C ox. So you only have this one number to worry about. Okay, so again, let me write it so that I can say equal to, put up a bit, is equal to WL C ox. Okay, so this C ox is just, you'll see this value. Okay, another thing that will, well, I don't know if I should mention this, but this, notice that this C ox, what the units of this C ox are, it's basically has to be units of, we're trying to get to a capacitance value. So Cox is gonna look like farads per sort of meter squared or farads per centimeter squared or something like that. It's in units of capacitance per unit area. That way, when you multiply it by the area, you'll end up with capacitance, which is what you're looking for. Now, another shorthand we do, I'm just giving you guys a heads up, that'll come in handy later, is that most of the time when you're doing digital design, you're going to keep the length at a minimum. Okay, so they end up giving you the capacitance, or even like pull the length also into the Cox at that point when we're doing digital design. But we'll see, and you'll get Cox's in farads per meter at that point as you pull in the length. You assume the length is constant and minimum for the process. But for now, let's just do area times this parameter Cox, which is the sort of the dielectric constant or the permittivity of the material divided by the oxide thickness. Okay, so that's the C here. So it'll be W times L C ox. Okay, now, so that's the capacitance. The second thing we need to know is the voltage. So this is like a real gross approximation, first level approximation, and I think a big part of the approximation, well, there's lots of things we're approximating here, but certainly one of the bigger ones is we're going to assume some average value of potential across this channel. Okay, this is basically this voltage here. At this point, it's the gate voltage minus the source voltage minus the VT. Okay, at this point. At this point, it's the gate voltage minus the drain voltage minus VT. Okay, so we're going to just assume that the entire channel is basically an average of these two values. Okay, so if we just look at let's see, if we just look at the voltages, so we're going to assume that the voltage is going to be, so we're looking for V gate channel minus VT. So at any one of these points, we're going to have a different V gate channel, but we're going to approximate all of that as an average value, which is V gate source minus V drain source over 2. Okay, minus a VT. So that's the average voltage across this channel, just the average value. And so the total charge ends up being, so if I take all of this, the total charge ends up being Cox W times L and then this voltage. So I'm basically saying I'm gonna plug in the C into here, and the voltage into here. So and the voltage is VGS minus VDS over 2 minus VT. Okay, so that ends up being the charge underneath the channel. So this was the first part of what we were trying to calculate for the current, which is the charge. And in my opinion, the biggest approximation we took was sort of what the actual potential voltage was. What's the voltage across this capacitor at every point in this channel? And we're approximating that as just the average voltage minus the threshold voltage, which is a pretty big approximation, as you'll see. okay? Because there's all sorts of electric fields here, and you know, it's not quite a clean geometrical picture as we've drawn here. So, but anyway, so just remember that this is really a level 1 model. So this is I would say this is a general enough of a statement to be true, right? Under all circumstances, the current is the charge and how fast the charge is traveling, the charge in the channel and how fast the charge is traveling across the channel. You kind of can't argue with that. It's just a general statement. So this will always be true. But what we're saying here is really a first level approximation. This model of how much charge there is under the channel and how fast it's moving has many levels of more complexity. So if you look at the SPICE models, as we'll use to simulate later, like a typical SPICE model for you know these processes like 0.18 micron or etc. is a level 49, and it's not like things stopped at level 49. This is just even pretty, you know, even older. So this is for, you know, circa a 0.18 micron process or 180 nanometer process. So right now, you know, the many levels go up. So basically my point being is that this calculation of this charge and also a calculation how fast it takes to go across gets more and more complicated. The deeper, just many layers of looking at this thing, and the smaller the feature sizes get in a particular process, it gets more and more, you know, you end up getting second, third, fourth order effects, etc. Okay, but we're still on our level 1 approximation, but I just wanted to make sure that you guys know this is not the be all and end all of, you know, this calculation of current in a MOS channel, and in fact it's a very simplified model. Okay, so now let's move on to the time it takes for the charge to go across. So again, we're trying to figure out current by charge divided by the time it goes across the channel. So let's now look at how long it takes the charge to go across the channel. Okay, so let me draw the dimensions here. We have, so this is the silicon dioxide, this is the poly, and this is the drain, and this is the source, and this is the length of the channel. Okay. And then we have a certain voltage V drain source just across the channel. And typically the source side is grounded. Okay, so in this case, the definition of electric field is the drain source voltage over the length. There's a negative sign here, but it doesn't really matter for our purposes, which is just that the negative sign just tells you which direction the electrons are moving, not how fast. Okay, so this is just a definition of an electric field, which is the potential voltage across 2 points divided by the difference, by the length between those 2 points. Okay, now we have a separate thing. So we have a velocity of electrons in a semiconductor, and they're related to the electric field with this parameter called mobility times the electric field. So mu is the mobility. And indeed, you have a different mobility. You have the mobility of electrons, and you have the mobility of holes, and they're different. So mu n is usually sorry guys, even I can't read my own handwriting, is usually 2 to 3x higher than mu sub p. Okay, so basically this thing is if you have an electric field and you have a velocity of the carriers from that electric field in a crystalline lattice, then you have this thing, you get this slope. As the electric field goes higher, the velocity gets higher, and that slope is the mobility. Now you also have a sort of a this doesn't keep going forever, does it? With the higher electric field, at some point you stop getting faster and faster, you sort of saturate, but we'll look at that later. But for the most part, for now, we're just assuming the velocity and the velocity of the charges going across the channel are dependent on the electric field with this parameter mobility. And then we can basically the total time across the channel is the length of the channel divided by this velocity. All right, so now we're gonna put, let's put everything together. So we basically said this is equal to the charge in the channel divided by the time it takes for the carriers to go across the channel. The charge in the channel is Cox W times L times the voltage, VGS minus VDS over 2 minus VT, times the 1 over time. Okay, so let's look at time here. Is length over velocity. The velocity is mu epsilon, so it's mu E. Okay, and then the E is mu VDS over L. So it's L squared over mu VDS. Okay, so if I plug this guy in to the time here, ends up being 1 over L squared over mu VDS, or redistributing all this stuff ends up being, so this, one of these L's cancels out with this L, this VDS goes up, so, and then I'm going to put all the constants together, so I end up with this mu Cox W over L, and getting all the voltages together. I'm going to bring the VT over there. Well, still keep VT minus VDS over 2 times VDS. Okay, so that ends up being the current IDS. So if we were going to draw, again, the curve of VDS versus IDS, this is at any point, poor choice of colors here, at any point here, as VDS is, and this is for a given VGS, right? At a given VGS, we plug that VGS in, the threshold voltage for the MOS transistor is, set value. And then as we sweep VDS across, we get this difference in current. And the current is, for a given transistor is dependent on the width over length ratio of the transistor times this, what ends up being a constant for each process of mu Cox. And so for a given transistor, we call all these parameters beta, or the gain of the current gain of the transistor, so that you have basically just IDS is equal to beta times the voltages. So you end up with this constant times all the voltages. Basically, that's your equation. And so notice let's look at a couple of things here. So obviously, like I mentioned, as this width over length ratio increases, that means as you make the transistor wider and wider and wider and wider, so this is the width. As this width increases, the more current flows across, which makes sense and is linearly dependent on that. So the wider this gets, the more current you can get across. So that's one. Okay. And then the higher the capacitance of the gate, the more control you have over the channel. And then this mobility is really the mobility of electrons, so it's mu sub n. So these two are really for a given process. But as your oxide thickness gets thinner and thinner, or gets smaller and smaller, the higher your current goes. So as your processes shrink, the more current you can also put across the channel. And then now let's look at this stuff. So now the higher your gate source voltage, the more the current. And the higher the VDS voltage, the more the current. So again, for each VGS, you get a current, but as your VGS gets for a different VGS, constant VGS, you will get a higher current. For a smaller VGS, you get a smaller current here. And as VDS increases, your current goes up. VDS increases, the current goes up. So that's what things look like in this linear part of this. Remember, we had another part that's saturation, but this is the linear part, okay? So again, real first order approximation. But first order approximation. I mean, it's first order, but really, really useful. I mean, for a lot of things, we end up using these values as, first thing just to calculate what kind of current to expect, do things make sense, those kind of things. Okay, so it's not, I'm calling it's a real simplified model, but it's not completely bogus. It's still useful. Okay, certainly gives you a feeling for why the curve is doing what it is doing. These actual values of like where the current is going to be off, as we'll see by second, third order effects, and we'll talk about those in the upcoming lecture. Okay, so now in this, what happens in saturation? Remember, this current in the linear domain, the current goes up as the drain voltage goes up, but at some point, this channel pinches off here, and you no longer have control. The drain source voltage no longer controls how much current you get because this channel is pinched off. So basically you just get this constant current after that point. So let's look at what that ends up being. So again, we have the gate, this is the poly, this is the oxide, this is the drain and the source, and here the voltage is VGS minus VT, and here the voltage is V gate drain minus VT. And at some point, which is VD sat is equal to VGS minus VT, at some point for the drain voltage, you basically get into this pinch off. Okay, so basically we can take this equation and plug in VDSat for VDS to see what happens at that point. Okay, so IDS is beta times VGS minus VT minus VDSat over 2 times VDSat. So all I did was so far is plug in VDSat for VDS to just get the value of the current at this point where the current versus voltage flattens out, and that's at VDSat. So I'm just picking that value. After this point, all the current stays constant at VDSat. Okay, and now VDSat is it's VGS minus VT is the value. So if I plug this stuff in here and plug in VGS minus VT for VDSat, move stuff around, I end up with beta over 2 VGS minus VT squared. Okay, you guys can do the math here. It's pretty simple. So, this interesting thing that happens here is you notice that there is no dependence anymore on VDS, just like, we'd expect from the curve. It's a flat curve, and it just changes with different values of VGS. And so there's no so in saturation, there is no dependence on VDS. So again, you get this flat curve like a current source. And what's the second thing? Oh, and then there's a VGS minus VT square law dependence. Let me just rewrite this. So square law dependence on VGS minus VT. So there's a very, very strong dependence on the VGS minus VT value as you increase the gate source voltage. Once you're past this threshold voltage, once the gate source voltage gets past the threshold voltage, you're increasing your IDS current very rapidly with increasing VGS. It's not just like if VGS, once you get past that point, if VGS minus VT doubles, you'll get 4 times the current, and so on. So you get much higher values. Okay, so now here's the summary of what we calculated. So I'm just putting all these things in one graph. And unfortunately, this is one of the things I don't remember too many things, but I'd certainly try to remember this, and hopefully it'll have this burned in my brain till my last days. And this is the Shockley first order transistor model, so we're talking about. So the first thing is when the gate source voltage is less than the threshold voltage, the transistor is off. There's no current flow, so that's just called cutoff. That's where we started. Then in the linear domain where VDS is less than VDSat, but so I have to say and VGS is greater than VT. So both of these conditions have to hold. We're in this linear model where we have this beta which is the mu Cox W over L. But then we still have this dependency on VDS in this. So it looks like a resistor. Like the higher the drain source voltage is, the higher the current. So let me just redraw this again. So VDS, IDS. So it's sort of up here in this linear domain. And then once you get past a certain point, VDS is larger than VDSat, and VGS is larger than VT. So both of these the transistor has to be on, so this has to be true. And VDSat is VGS minus VT. Then you get this flattening of the curve. So end up here. And you no longer have a dependence on VDSAT, but you have a score law dependence on VGS minus VT. Okay, so let's look at an example. This is a pretty old process. This is a 0.6 micron process. And it's giving you the TOX, the mobility, the threshold voltage. So this is pretty typical. When you get a process, when you're designing in a process, these are given values. Okay, you'll get this from the manufacturer. It's in the in the SPICE models, if you know where to look, or you might have to calculate them a bit, but you can get these values. Okay, and then you can basically go about with these values as a first order model. You can go about calculating the current versus the drain source voltage. So we want to calculate the current versus the drain source voltage. And so you plug in all the parameters. This is the mobility, 350. By the way, be really, really careful, as always, with your units. Some of these are given in both farads per meter squared, farads per centimeter squared. This is the mobilities in terms of centimeters squared. So you got to be a little careful here to use the right permittivity number. And then you have the width over length of the device, which is given here. One interesting thing, by the way, notice that the current depends on the ratio of the width over length. So it means as if you have a very wide but a very long transistor, you'll get the same current out of it as a less wide, less long transistor, as long as those ratios are the same. Okay, so the first thing you actually do is you end up calculating this beta value, because that stays constant for all the voltages. Okay, you're just basically calculating this, so you can just multiply it by the voltages as you basically sweep these voltages across. And you'll see this very familiar parameter. So at different VGSs, as VGS increases, notice how VGS from, I guess this is VGS of 1, so this is the device is barely on, to VGS of 2, there's a big jump in current, and also big jump in current from 2 to 3 and so on, because you have in these areas, this is in saturation, so you have a square law dependence on VGS minus VT. So the current just jumps up quite a bit as your VGSs go higher. Okay, and after this VDS value, at every point VDSAT increases. So here VGS is 5 volts. So here VDSAT is 5 volts is VDSAT is 5 volts minus VT, or 5 volts minus 0.7 volts, or 4.3 volts. So notice it's sort of up out here where you get this inflection from the linear into the saturation. Here, VGS minus VT is only 2.3 volts. So VDSAT for this guy, when VGS is 3 volts, is 2.3 volts. So here, the inflection point is further down here. So you get this linear here, saturated here, this linear, so-called linear, linear but non-linear region goes quite a bit longer and then saturates in the end. Okay, so that's an example. And it turns out, so that's all the stuff for NMOS. It turns out all the stuff for PMOS ends up being reverts. So all the voltages are inverted, the current direction is inverted. So now you're thinking in terms of VDS being VDS being negative. Notice all these are negative values. So if I was going to plot a NMOS curve here, so this would be VDS, NMOS curves would kind of do like this. Whereas the PMOS curves do this. So as VDS gets more negative, you start saturating. And as VGS gets more negative, you get more current flowing. So this is the nature of the PMOS. Now, one of the main things this is very important, that remember that you have to remember that these curves are going, everything is kind of reversed compared to an NMOS. So you got to really keep track of, when you're doing calculations, you have to make sure you keep track of your voltages, signs, and all that stuff. So you're adding things with the right signs, because you could end up, going the wrong direction, obviously, and get your currents too low or too high if you're not careful about the sign of your voltages. So that's the one thing to worry about. Second thing to remember is that, as I mentioned, the mobility of PMOS is usually 2 to 3x lower than NMOS, which means that beta of a PMOS is beta of NMOS over 2, or let's say 2.5x, okay? That means if you wanted to have a PMOSFET having the same current as an NMOSFET, you would need to make the one control you have over the beta, so you don't have any control over the mobility or COX. The length in a digital process, you'd like to keep it minimum, because as you increase the length, the only thing you're doing is slowing yourself down and increasing your area. There's really not much benefit for a digital device. So you can basically play with the W. So the width of a PMOS to have the same current as an NMOS typically needs to be about 2 or 3 times bigger than the width of an NMOS to give it the same current at the same voltage, etc. Okay, so I'm gonna stop here, and then I'll follow up with the capacitance. I think there's more I want to say about the capacitance, and I'll stop here for now.